Hi, I am Sushma, working as Assistant Professor in the Department of ECE in Institute of Aeronautical Engineering College. In this session, we are going to discuss about the multi-level NAND NOR realization circuits. So here, in this session, we are going to discuss alternate logic gate representation, convert AOI logic to NAND logic, and AOI means AND OR inverter, convert AOI logic to NOR logic. We will do some examples of NAND NOR realization. So first, we have to know what is the procedure to convert the AOI logic to NAND NOR realization. So here first we have to draw the logic circuit using AND OR NOT gates only. So whatever the circuit, whatever the equation, Boolean equation is there, we have to write that equation and we have to draw that logic circuit using AND OR NOT gates only, because here we are converting AOI logic to multi-level NAND or NOR realization. AO means AND, O means OR, I means inverter. So whatever the Boolean function, we have to represent that into logic diagram in terms of AND OR inverter gates only. So if you want to convert AOI logic into NAND logic, so here we can convert the AOI into either NAND realization or NOR realization. If we want to convert that total circuit, we have to represent in terms of only NAND gates. Then first step, we have to add a circle at the output of each AND gate. So if whatever the circuit AND gates there in the circuit, we have to add the circle at the output of the each AND gates. For how many, if we have 2 or 3 AND gates, we have to add, for every AND gate we have to add circle, that is bubble at the end of the gate, each AND gate inputs to, and we have to add bubble to the inputs of the OR gate for NAND realization. So if for AND gates we have to add bubbles at the output. If we have OR gate in that, we have to add bubbles at the input. Okay, so if we want to convert AOI logic into NOR logic function, so if we want to convert that into NOR logic function, so first whatever the Boolean function is there, we have to draw that in terms of AND or NOT gates. In that Boolean expression, if we, in that logic circuit, if we have AND gates and OR gates and NOT gates, for a NOR realization, for NOR logic, so we have to represent that Boolean function, we have to represent in terms of only NOR gates in NOR realization. So in this, if we have the OR gate, we have to add bubble at the output. Okay, if we have AND gates, we have to add circular, that is nothing but bubble at the inputs of the all the AND gates. If it is NAND logic, draw the AOI logic circuit. If we have AND gate in NAND logic, we have to add bubble at the output side, and OR we have to add bubble at the input side. So this is the difference between NOR logic and NOR logic. In second step, we have to add or subtract an inverter on each line that received a circle in step 2. So if we are adding bubble at the output side, the AND gate, here we have to add one inverter. Okay. So if we are adding bubble, circular bubble at the input side, so here we have to add inverter in this line and another inverter in the, because we are adding here 2 bubbles. So for NOR also, here we have to add one bubble input side. Wherever you are adding bubble in that line, we have to add one inverter. So this is in step 2. Okay. So that polarity of the signals on these lines remains unchanged from that of the original diagram. So again, if we have 2 inverters in the same line, we have to remove that inverters, and we have to represent the whatever the inverters are there. We have NOT gates. We have to represent that in terms of NOR for NOR logic and NAND in NAND logic. So this is the procedure to convert the AND or invert logic circuit into NAND or NOR realization. In NAND and NOR realization, if it is a NAND realization, the circuit should be represented by only NAND gates. If it is NOR realization, the logic circuit should be represented in terms of only NOR gates. So before going to discuss about the NAND realization logic, so here we will discuss alternate logic gate representation. So we have gates, AND gate, OR gate, NAND gate, NOR gate, or NOT gate. These are the basic gates. So here we have to represent another alternate logic gate representation for those gates. In some networks, they will use alternate circuits of these gates. So first we will see how to represent alternate logic gate representation. So here the basic gate here, and or NAND and NOT gates, we will see the alternative logic gate. So first we have to use De Morgan's law. Okay, so this is AND gate. A, B are the inputs, Y is equal A into B. Okay, so how we have to represent alternate logic gates means here we have to apply De Morgan's law. De Morgan's law is Y is equal A dot B whole bar. I am writing here. So this I can write this as, what is De Morgan's law? Y is equal A into B bar is equal A bar plus B bar, and Y is equal A plus B whole bar is equal A bar into B bar. Okay, so here we can write A bar B bar, we can write that as A bar plus B bar whole bar. So that is nothing but Y is equal to AB. Whole bar is nothing but, that is nothing but AB only. So that we can write as A bar plus B bar whole bar. So this circuit we have to represent on an alternate logic gate. So A bar plus means here we have to use OR gate, and we have inverter NOR gate. A plus B whole bar is NOR gate. Here A bar B bar we have. So A bar means A, we are giving bubble, that is inverter input we are giving. B, we are giving invert input. So here A bar B bar. So here A bar plus B bar whole bar, that is nothing but A by whole bar, that is AB. So the alternate circuit for AND gate representation A, B, Y. So this is the alternate circuit for the AND gate, that is bubbled NOR gate. This is bubbled NOR gate. Okay, so this is the equivalent circuit of the AND gate. So next, second one is OR gate. So in OR gate, okay, so here in OR gate, this is OR gate A, B, Y. So we can write that as Y is equal to A plus B. So here we are going to apply De Morgan's law, that is nothing but A plus B whole bar. Apply De Morgan's law here. So A plus B bar whole bar is nothing but A plus B only. So here we discussed here Y is equal to A plus B whole bar. We can write that as A bar into B bar by using De Morgan's law. So here A plus B whole bar, apply De Morgan's law, A bar dot B bar whole bar. So here AB whole bar is nothing but NAND gate. So here NAND gate, A bar we are giving. So we have inputs A and B. To get A bar, here we have to give one bubble. So that is nothing but we are inverting A input. So that is here internally it is A bar and B bar it is taking as inputs. So we can write that as A bar, B bar, NAND operation whole bar. So that is equivalent to A plus B whole bar. Okay. So the OR gate, alternate logic representation of OR gate is nothing but, so here we can represent A, B, Y is equal to A plus B. We can draw that equivalent circuit. We have to make R is AND, add bubbles. If we don't have any bubbles at the input and output side, we have to, if it is R, we have to draw AND. Input and output side, if we don't have any bubbles, add bubbles at the input and output side. So A, B, Y. So this is equivalent circuit, that is A bar dot B bar whole bar is nothing but A plus B whole bar. So this is equivalent circuit of the OR gate. Third one, NAND gate. So here in NAND gate realization. So in NAND gate, this is the NAND gate. A, B, Y is equal to A, B bar. We can apply De Morgan's law. We can write this as A bar plus B bar. So what we discussed earlier, if we have AND gate in equivalent circuit, draw OR gate. If we have bubble, here we don't need to keep the bubble at the output side, because here the output side we have bubble. Input side we don't have bubble, so keep bubbles in the input side. A, B, Y, we can write this as, if we have A is given to the bubble, means A bar plus B bar. That is nothing but AB whole bar. Okay. So here another gate is NOR gate. NOR gate is this one. So in NOR gate, A, B are the inputs, Y is output. So here we can write A plus B whole bar. Apply De Morgan's law, we can write A bar into B bar. So the equivalent circuit for this one is, so directly we can draw by saying this one without applying the logic also. If we have OR gate, draw in equivalent circuit AND gate. If we have bubble at the input side, we don't need to keep the bubble at the output side. If we don't have bubbles at the input side, we have to add bubbles at the input side. So this is A, B and this is Y. So we can write A bubble. We are giving A is given to the bubble, that is A bar and B bar. So A bar dot B bar. This is AND gate now. So input for this we given A bar and B bar. So it is AND gate. We are multiplying A bar into B bar. We can write this as A plus B whole bar. Okay. Otherwise directly we can draw A bar dot B bar. Dot means AND gate. A is given to the bubble, B is given to the bubble, and output Y is equal, we can write A bar dot B bar. So these are the alternate logic circuits, and another one is NOT gate. NOT gate, we have one input and one output. If we are giving A, we can write A bar. So this is equivalent circuit. So this is A bar, we are giving to the buffer, that is we are going to get A bar. So if we want to represent NOT gate in terms of NAND and NOR realization, so NOT gate, so here this is equivalent circuit for the NOT gate by using NAND, because here normally Y is equal NAND gate means, what is the NAND gate equation? Y is equal A dot B whole bar. Okay, so here I am giving both inputs are A and A. So here I can write A dot A bar, that is A bar. Nothing but we can draw the equivalent circuit for NAND gate is, if we give both inputs are same A and A, we can write that as Y is called A into A bar. A into A is nothing but A, we can write A bar. So this is, here we are going to invert operation of A. So this is equivalent circuit of the NOT gate using NAND. Okay. Another equivalent circuit for the NOT gate using NOR is, NOR also here, this is NOR gate. Here I am giving both inputs are A. So that is nothing but I can write NOR gate is A plus B whole bar. So both inputs are A only. So A plus A whole bar. A plus A is nothing but A. We can write that as A bar. So here we are, by if we give input A, we are getting output A bar, inversion operation. So this is NOT gate using NOR and NOT gate using NAND. So if we know these alternate gates, we can easily realize the NAND and NOR realization. So here we will take one example, AND or invert logic to NAND NOR logic. Here we are going to implement exclusive OR gate, that is XOR gate using NAND gates. Okay. So what is the equation for the XOR gate? Y is equal AB bar plus A bar B. So in step 1, in NAND realization, first we have to take this Boolean function and we have to draw the logic for this Boolean function in terms of AND or inverter only. Okay. So that's why A, B is given to the inverter. We are going to get A, B bar. So A into B bar given to the AND gate. So here we are going to get A into B bar. And A bar is nothing but A bar we can write. If we give A input to the NOT gate, we will get A bar and B. So both here we are going to get A bar into B. If we add these two outputs, A B bar plus A bar B, we will get the XOR gate operation. Okay, that is A B bar plus A bar B. So in this Boolean function, if we draw that logic circuit, here we have only AND or inverter. So we have to draw the Boolean function in terms of AND or inverter logic. First step. In step 2, if it is NAND realization, we have to add bubble at the outputs of the AND gates and we have to add bubbles at the input of the OR gate. So here we have two AND gates, one OR gate. So first we have to add bubbles at the output of the AND gates. And bubbles at the input of the OR gate. So this OR gate we have to add bubbles at the input side. Okay, in step 2. So in step 3, what we have to do? In step 2, what we have? We are adding bubbles at the AND gate at the output side. Bubbles at the input of the OR gate. Okay. So in step 3, wherever we are adding bubbles, in that line we have to add, for each bubble we have to add one inverter. So in this line we are adding one bubble at the output of the AND gate and input of the OR gate. In this line, for each bubble we have to add one inverter. So here A, B, so here we are adding one bubble. We added one bubble. So here we have to add one inverter. And for OR gate also in the same line, we are adding two bubbles. So another inverter we have to add here. Okay. So A, B. In here also we are adding two bubbles in this line. So we have to add two inverters. Wherever we are adding bubble in that line, we have to add one inverter. We should not change this bubbled OR and NAND gates. Okay. In step 3, here we are adding two inverters. So if we have two inverters in the same line, remove these inverters. Okay. And realize this NOT gates in terms of NAND, because we are implementing XOR gate using NAND gates, NAND realization. So in step 4, A. So inverter also we have to represent in terms of NAND gate only. Here this is the inverter. In the inverter we can represent in NAND gates. This is A bar. Here also we are going to get A bar. Okay. So every gate should be represented in terms of NAND gates only in the NAND realization. So we have two inverters in the same line. We can remove these two inverters. So if we have back to back in the same line. Okay. So the equivalent circuit for the bubbled OR Gate is nothing but here we can draw. If we have OR gate, we have to draw, and we have bubbles at the input side, so we should not add that bubbles in the input side. We don't have bubble at the output side, so here we can add bubble at the output side. So the equivalent circuit is this one. If we have A, B here Y is equal A bar plus B bar, that is nothing but AB bar. So here also A, B, Y is equal AB bar. So these are the two equivalent circuits. Bubbled OR is equal to the NAND gate. So here we have bubbled OR gate, so we can represent that in terms of NAND gate. So this is the, here if we see this XOR here, this is the XOR operation of Y. Here each gate is represented in terms of only NAND gates. NAND realization of XOR gate. Okay. So if we want to represent exclusive NOR gate using NOR gate realization. So here Y is equal, here we have to implement XOR, we will see XOR gate using NOR realization. Previous problem is about the XOR gate using NAND gate realization. Here, okay, so that is nothing but A XOR B is equal AB bar plus A bar B. Okay, so in NOR realization, first we have to implement, in step 1 we have to implement that boolean function in terms of AND or inverter logic. So we have to draw AND or inverter logic here. A B bar is NOT gate to the AND gate, and A B so here that is A XOR B. Okay, in NOR realization, in step 2 we have to add bubbles. In NOR logic we have to add bubbles at the input of the AND gate. The bubbles circles at the input of the AND gate, and for OR gate we have to add bubbles at the output side. So in step 2 we have to add bubbles circles at the input of the AND gate, and for OR gate we have to add bubble at the output side. Okay, in step 3 here we added bubbles at the input side. In each line, if we add bubble in that line, we have to add one inverter. For NOR gate, we are added bubble at the output side. So in that line, we have to add one inverter. So here, if we are adding bubble in this line, we have to add one inverter here. Here we are adding already one inverter is there. We are adding one bubble here. So here we have to add one inverter. So in this line, we have got the two inverters. So we should eliminate these two inverters. If we have back-to-back inverters in the same line, we have to eliminate that one. So in step 4, each gate, if we have a NOT gate and any bubble AND gate, we should represent that in terms of NOR gate, because we are implementing XOR gate in terms of NOR realization. So each gate should be represented in terms of NOR gate only. So A, B, bubbled OR is equal to the NOR gate. We will see here. Bubbled AND gate is nothing but A, B, Y is equal bubbled A bar dot B bar, that is nothing but A plus B whole bar, is equivalent to A, B. If we draw directly, AND will become in equivalence and OR. If we don't have bubble at the output, we have to add at the output side. If we add bubbles at the input side, we should not add the bubbles at the input side here. So this A plus B whole bar is nothing but NOR gate. So here bubbled AND is nothing but NOR gate. In here we have one inverter, so that we should represent in terms of NOR gate only. So bubbled AND is NOR gate. Here also this one NOR gate. Inverter we should represent in terms of NOR gate only. So this is Y is equal A XOR B by using NOR realization. So each gate represented by NOR gate in NOR realization. So this is the procedure for the AND or XOR and by using NAND realization and NOR realization. So here A plus B C into whole bar into D. So first this equation we have to represent in step 1. First F is equal, the equation is A plus B into C complement into D. So first we have to implement this Boolean function into AND or inverter logic. So here A, B will be given to the OR gate, okay, into C into, and here we are getting A plus B. Here A plus B is multiplied by the C and the complement is NOT gate, and here we have to multiply that with the again one AND gate D. So here finally F is equal A plus B into C complement into D. So this we have to realize in terms of NAND and NOR realization. So in the step 2, first we will see NAND realization. Okay, in NAND realization what we have to do in step 2? We have to add bubbles at the output of the AND gate and input of the OR gate in the NAND realization. So here A, B, so OR gate, we have to add bubbles at the input side. For AND gate, we have to add bubble at the output side. Okay. In step 3, directly I am drawing here. So in step 3, if we add bubble in that line, we have to add one extra inverter. So A, B, here we have to add one inverter because we added a bubble in the now bubbled OR gate. C, here we didn't add any bubble in this line, so directly we given to the AND gate. Here we added one bubble, so I add one inverter here. And in this line also we added one bubble here, so add one inverter here. Okay. In step 4, what we have to do, if we have any extra back-to-back inverters, we have to remove those inverters, and each gate we should represent in terms of and NAND realization. So NOT gate also we have to represent in terms of NAND gate. So bubbled OR is equal to the NAND gate. Here we removed these two inverters because we have back-to-back inverters in the same line, so we have to remove the inverters. And NOT gate also we have to represent in terms of NAND gate. This is F. So here each and every gate is represented by NAND gate only. So this is how we have to implement Boolean function into NAND realization. So same equation we have to represent in terms of NOR gates. So what is the equation here? F is equal A plus B into C complement into D. So first we have to we have to represent this by using NOR logic realization. Okay, so here in step 1, first we have to implement this Boolean function in terms of AND or invert logic. So A, B is given to the OR gate. Here we are going to get A plus B into C. Into means we have to given to the AND gate. So here we have complement. So we have to draw NOT gate. Then into D. So total here we are going to get here A plus B. Here A plus B into C. Here A plus B into C whole complement. Here A plus B into C complement into D. So this is the equation. We are representing in terms of AND or invert gates only. In step 2, what we have to do in NOR logic realization, we have to add bubbles at the output of the OR gate and bubbles at the input of the AND gate. So we have 2 AND gates and 1 OR gate. So here A, B. So for NOR realization, we have to add bubbles at the output side and bubbles at the input of the AND gate. So this is F. Okay. In step 3, what we have to do? We have to add inverters at the each line of the. If we add bubble, then we have to add one inverter in that line. So here in step 3, first NOR gate. So this is F. So in step 3, we have to add bubbles at the each line where we are adding in that line. So in step 3, so here we have to add one inverter here. We have 2 bubbles we added. So I added 2 inverters here. Here also I have to add one inverter. Here also, because in that line I added one bubble. Here also we have to add one bubble. So here we have back-to-back inverters. We have to eliminate those inverters and bubbled AND is equal to the NOR gate. So in step 4, each gate should be represented by NOR gate only. So A, B is given to the NOR gate and C, we have an inverter that we should represent in terms of NOR gate. Bubbled AND gate is nothing but NOR gate. Bubbled AND gate is A, B, A bar into B bar, that is nothing but A plus B whole bar, that is equivalent to the, if we have AND, we have to draw R. We don't have bubble at the output side, we have to add bubble. We have the bubble at the input side, we should not add bubbles at the input side. So A, B, that is Y is equal A plus B whole bar. So same equation we are getting here. So bubbled AND is equal to the NOR gate and D we are given to the inverter that we should represent in terms of NOR NOT gate. So bubbled AND is nothing but NOR gate. So here this is F is equal A plus B into C complement into D. So here in each and every gate is represented by NOR gates only. So here these are the examples for AND or invert logic to NAND or NOR logic. So the books I followed is John F. Wackerly, Digital Design Principles and Practices and Modern Digital Electronics by R.P. Jain. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.